The mass spectrum for 2-hexanone is shown below. Which fragment represents the base peak? So we need to define the base peak. So this is the tallest peak in your spectrum. And that tallest peak corresponds to 100% relative intensity, it's labeled here, or this could also be labeled as relative abundance. So it is the ion that is seen the most by the detector in this particular mass spectrum. So the tallest peak, the one at 100% abundance. And so then we want to also, to identify it, we want to recognize what these numbers mean. So 43, what that is the m over z value, which is the mass to charge ratio. So what happens in a mass spectrometer is you have a molecule. It is hit with a high energy beam of electrons, and this knocks one electron off of your molecule to give you your molecule as a radical cation, and this is known as the molecular ion. And this is typically the heaviest peak in this spectrum. And so the molecular ion peak is this peak here at 100. That is the molecular ion, sometimes abbreviated as M+. And if you were to add up the mass of 2-hexanones, so count up all the carbons and hydrogens and oxygens and tally up the molecular mass, you'd find out that it weighs 100. And so these numbers correspond to the weight of the ion, okay? So all of these values are the weight of the ion. So our base peak has a mass equal to 43 atomic mass units, okay? So the first thing that I would do in considering this, there's a few approaches you could take. If you wanted to just go the mathematical approach, you could simply calculate the mass of every one of these fragments and find out which one weighs 43. That would be a way to do it. Another way to look at this is the common fragmentations that we see. So this molecular ion itself is not going to be stable typically. It's going to break down further, and when it does that, you get some parts that are cation, and the radical typically goes to the other side. And it is the cations that show in the spectrum. Because your mass spectrum is only going to show the positively charged ions, and they're always going to be a +1. So if we know how different functional groups break down, we can take a more rational approach than just calculating the weight of all of these fragments. So we have a ketone, and what ketones tend to do is they tend to undergo alpha cleavage. And this happens with a lot of functional groups. So what I would expect to see is so let me redraw my 2-hexanone down here. These are the major pathways that I would check. I would expect that I would see cleavage maybe here, and what that would do is give me this resonance stabilized fragment, and the rest of the molecule we've lost there, the methyl group, would be a cation, so this would not be seen by the detector. The methyl group would be a radical. It would be just the cation that is seen by the detector. And you could add up the weight of this entire fragment. You might notice that this is the same as what's drawn here for A. A common way of doing this is to calculate what this fragment is based on what was lost. That would be a fast way to do your math. And so a methyl group weighs 15 mass units. So I would expect this to be at M minus 15, and we said our molecular ion is 100. So this particular fragment is corresponding to what we see here at 85, okay? And so that's not the base peak. So the next logical thing to do would be to look to the other side of the carbonyl. And so we can redraw this molecule again and say, okay, what about cleavage here? Okay, and so I would consider that we're going to get the resonance stabilized cation, so that would be this cation, and we have lost this butyl chain as a radical. And in this case, I mean, the butyl chain's a little bit larger. Your fastest way to go about calculating the mass of this particular ion might just be to come up with the molecular formula. So this is C2. We have 3 hydrogens out here. There is not a hydrogen on the carbonyl. That's where we broke the carbon-carbon bond. So there's just those 3 hydrogens, H3O. And if you were to add up this mass, right, so 2 times 12 for the carbon atoms, 3 times 1 for the hydrogens, 1 times 16 for the oxygen. And if you add that up, you're going to find out that that weighs 43. So that means that this is our base peak. This is what we're seeing. And it makes sense for this to be the base peak because we've got this nice resonance stabilized cation. So that here is option C.